What's up, everyone? Today we're going to talk about exponential applications. So let's get into it. All right, so first up, there's two different types of exponential applications that you'll see. One where it's indicated that it's increasing and one where it's indicated that it's decreasing. These formulas aren't given to you, but they're very similar to something we've already talked about before. All right, so with both of these formulas, the P in each is the principal or the starting amount. The R is the rate or the decimal of the percent, and the T is the time. Note that these are both very similar to the geometric sequence formula that we've already used. The main difference between the geometric sequence formula and these formulas is two main differences. One, that it explicitly tells you whether the rate is increasing or decreasing, but also more importantly in the exponent, you'll notice that it's just t or just the time. You're not subtracting 1 from that value like we did in the geometric sequence formula. So therefore, biggest question is, well, which one do I use then? It really doesn't matter. They both work the same way. These might be more useful when the problem says after, like after 8 years, so you don't have to remember to add 1 to it. If it said after 8 years for these problems, you would just sub in 8 for your time and be good to go. So let's do a couple examples. Oops. Right, example number 1, we have 6 pairs of bears. So actually, even before I get further into this, I'm going to note that 6 pairs, pair meaning 2. So I'm actually talking about 12 bears total. So 12 bears were introduced to a large island off Alaska where previously there were no bears. So we now know that these are the only 12 in existence on this island. It is expected that the population will increase by 14% each year after the introduction. So this tells me that my rate is 14%, or as a decimal, 0.14. So in part A, they're asking us to write a model, aka an equation, for the number of bears, B of t, on the island t years after the introduction. So they're just asking us to write a general formula. So I'll have my B of t, since that's what they asked me to use. My initial starting value, or the principal value, is those 12 bears they introduced. It says increase, so that means 1 plus whatever the rate is, so 0.14, raised to the time. Obviously, we know we should be simplifying our answers, so our final answer for this one should be the B of t equaling 12 times 1.14 raised to the t. Part B, finding the population after 7 years. So again, after 7 years, these problems account for the after part. In geometric formulas, we had to say, okay, now we're looking at 8 years because then we subtracted 1 in the exponent. There is no subtraction here in the exponent, so that means it's a little bit easier. I know it sounds kind of confusing, but it actually is easier because that means I can just sub in the number that they give me. So I can just sub in that 7 for t and evaluate it from there. And when I evaluate that, I get 30.027, etc. So we know IB likes 3 sig figs, but we also know that you can't have, you can't have 0.0 a bear, but we also know that bears or animals or humans, we should be rounding to the nearest whole numbers. So I could round this either, and IB would accept either, 30 bears or 31 bears. Part C, asking how long will it take the population to reach 100? So now notice they changed the information they gave you. We're now looking for t, and they gave us the number of bears. So now instead of subbing in 100 for t, I'm subbing in 100 for the B of t, or for B. So I'll say 100 equals 12 times 1.14 raised to the t. Several ways you can solve this. One way, and the easiest way for me right now, is to use Desmos. All right, so in Desmos, what I'm going to do is I'm going to type this 100 into the first y. I'm just going to call it y1, and type the right-hand side into y2. So in Desmos, I'll have 1y equaling, I'm going to say y equals 100, just because Desmos needs to be specific what equals 100. And in y2, I'll have my right-hand side of the equation. Again, just like a calculator, subbing an x for t instead. So from my home screen or my home graph, that doesn't really help me much. But if I zoom out, because remembering my first y equaled 100, so zooming out until I can see that, you're looking for the intersection point. So I'm looking at this point right here. So 16.182 is my answer. You could also do this in your TI, where you could do the same thing, find the intersection point, or you can use the table instead. All right, so again, adhering to some IB rules, that I could say this is 16.2 years. IB would also take 17 years. Because if you use the table, that would be that first place where the population would reach 100 or surpass 100. They wouldn't take 16 years just because if we rounded that 16.2 down, I technically haven't reached the population of 100 yet. So that would be a reason to round up even if you used, just like we did, the intersection method and then rounding it up to 17. But they would take either of these. All right, in example 2, the population of turtles in a lake sadly decreases by 7% each year. So that tells me that my rate is 0.07 because of the decimal. In 2005, there were 340 turtles in the lake. So that tells me my principal or my primary amount was 340. So in part A, writing an exponential model for the number of turtles, t, in the lake n years after 2004. So just keep that in mind maybe for future parts of this question. So my exponential model, t equaling my primary amount or my principal amount of 340 turtles times, since I'm decreasing by 7% each year, I'm doing 1 minus 7%, or that 0.07 raised to the n. So again, just simplifying inside parentheses, and you could have done this all in the same step. Part B, how many turtles were in the lake in 2010? So again, remember, n is equal to the number of years after 2004. So that tells me that 2010 is 6 years after 2004. So n would have to equal 6. So I can just use the equation that I got in part B and sub in n equaling 6. And evaluating that in my calculator, get 219.976, et cetera, et cetera. So again, talking number of turtles here, so it should be a whole number. So IB/me/I would accept either 219 turtles or 220 turtles. As long as it's a whole number that's one of those two because of the rounding, that would be fine. In part C, if the population falls as low as 10, so they're talking about the number of turtles equaling 10, conservationists will not be able to save the turtle colony. And according to your model, when will this occur? So very similar to example 1, they're now giving us the number of turtles, or in our case, t, and they're wanting us to solve for when is that going to happen. So we're solving, in our case, for n. So I'll go to Desmos, So, I mean, you can play around with your graph if you need or want to. I don't really need to, just because if I click on one of the graphs, my gray dot as my intersection pops up in Desmos. So I'm looking at x or n equaling 48.592. So because of the type of question they're asking, our answer can look several different ways. They're asking, when will this occur? Just saying n equaling 48.592, what does that even mean? You could say, again, rounding to 3 sig figs at least, I could say that this will happen 48.6 for 3 sig figs years after 2004, right? Because that's what n represents, the number of years after 2004. I could say the same thing, but 49 years after 2004, because again, until I've hit at least 48.6 years after 2004, it won't reach as low as 10. So that's why I would have to round it up to 49. Or if I use the table in my TI calculator, I would get 49. And we could also figure out what is, in that case, 49 years after 2004. So I could also say in the year 2053 is when it would happen, since that would be 49 years after 2004. Note that if you do write it that way, saying 2052.6 doesn't make any sense. That's not a year. So if you do choose to write it in that capacity, just make sure you do round it to the nearest whole number.